In 1928, a young man shuffled onto a stage in Germany to present a lecture on his recent work. He had a slightly unusual presentation style. Physicist Eugene Wigner described the lecture as detached, almost like a recitation of a technical text. He said the man spoke without giving any sign of enjoying his own lecture. But the work this strange, unassuming man presented was about to send some of the most famous quantum physicists of the 20th century spiraling. After the lecture, Werner Heisenberg described the man's theory as the saddest chapter in modern physics. Heisenberg also wrote to Niels Bohr and said, "I find the present situation quite absurd, and on that account, almost out of despair, I have taken up another field." Legend has it that Wolfgang Pauli even announced that he was abandoning quantum physics, and then he started writing a utopian novel. What had the young man said to disrupt the world of quantum mechanics so profoundly? Well, he had been working on a problem that physicists are still tackling today, the unification of Einstein's relativity and quantum mechanics. And his work had revealed something troubling. A particle unlike any seen in the world. A particle with negative energy. In 1905, Albert Einstein published his special theory of relativity. It was based on the simple idea that for anyone moving with constant speed, the laws of physics should be the same, and this includes any measurement of the speed of light. So it doesn't matter how you're moving relative to a beam of light, you should measure its speed to be 300 million meters per second. This means that things that we ordinarily think of as fixed, like time and space, have to transform so that the speed of light is always measured to have the same value. In making this discovery, Einstein realized that space and time are not really separate dimensions at all. They're linked in a four-dimensional fabric called spacetime. When Einstein applied this idea to an object emitting light, he found something peculiar. When an object loses energy by emitting photons, its mass must also decrease, and the change in the object's mass is equal to the energy of the photons emitted divided by the speed of light squared. In other words, he found that energy must be equal to mc squared. E equals mc squared.
Mass and energy are but different manifestations of the same thing.
So a particle's total energy comes from its momentum and its rest mass, giving a new relationship between energy and momentum. Now, if we take the square root of both sides, we get an expression for the energy of a particle in terms of its mass and momentum. And if we plot energy versus momentum in a single dimension, we get this curve, where mc squared, the rest mass energy of the object, is the lowest possible value for energy. But really, when we took the square root, we should have put a plus minus out front, which would give us two curves, one for positive energies and another for negative energies. But we don't observe things that have energy less than zero. I mean, what would that even mean? So in classical physics, the solution is simple. You just ignore the negative energy solutions. They can't physically represent anything, right, Casper?
Well, sure, that sounds right, but around the same time that Einstein was coming up with his special theory of relativity, physicists began observing some strange phenomena in atomic physics that were overthrowing all of these classical assumptions. First of all, they noticed that when looking at the energy levels of subatomic particles like electrons, they weren't continuous at all, they were discrete. And they also didn't just behave as particles, but as waves. So if you would take electrons and fire them through two narrow slits, then they would create interference patterns, just like light does. What they were discovering was the new field of quantum mechanics. And in 1926, Erwin Schrödinger formalized this field by coming up with his now famous wave equation, which describes how quantum mechanical systems evolve over time.
This was the most radical new theory of the 20th century and would remain so. This is not a bit like Newton or a bit like Maxwell. This was radically new.
The equation solution, called the wave function, psi, does not describe a particle with a precise position and momentum, as classical laws would, but instead the modulus squared can give us the probability of finding the particle in a specific location at a specific time.
Deriving the Schrödinger equation is actually surprisingly simple. Just start by writing down the total energy, which for a free particle is just its kinetic energy, half mv squared. And we can rewrite it in terms of momentum, mass times velocity. So kinetic energy is just momentum squared divided by 2m. Now we're going to make this quantum. And to do that, we need two things. The first is the wave function, psi, which describes how particles act as waves at quantum scales. And the second is something called a quantum operator. This is just a mathematical tool that extracts information from the wave function to reveal a specific property of the particle, like its position, energy, or momentum. The operators for energy and momentum look like this. By inputting these operators, we can make each side of the equation act on the wave function. And that gives us the Schrödinger equation for a free particle. For particles that aren't free, like electrons in atoms, you need to factor in potential energy too, which gives you the full Schrödinger equation.
But there are some places where it doesn't produce the right prediction. For example, take the element gold. The Schrödinger equation suggests that it should be a silver-gray color, just like all the other metals. But it's not. I mean, it's gold. And for mercury, the Schrödinger equation predicts that it should be a solid at room temperature, but it's a liquid. So what is wrong? Well, I'll give you a hint, because both gold and mercury are heavy elements.
They have a high number of protons in their nuclei, which attract orbiting electrons more strongly. So if you're thinking in a classical sense, the electrons would be bound tighter in, and they'd be whizzing around at higher speeds than in other elements. And for electrons in some orbits, those speeds start to get a little too close to the speed of light. So let's go back to the Schrödinger equation. There we had the kinetic energy was p squared over 2m. But for particles moving at relativistic speeds close to the speed of light, that equation isn't the right one. The correct equation is the energy-momentum relation from special relativity.
Schrödinger's equation is not consistent with the theory of relativity, so technically it's not right.
So the solution seems simple enough. Just start with the relativistic energy-momentum relation and use that to derive a new wave equation. Well, this is exactly what a physicist named Oscar Klein did in 1926. He subbed in the same energy and momentum operators that Schrödinger used and found this equation. Klein's work was pretty well received by a number of his colleagues. In fact, it turned out that two other physicists, Walter Gordon and Vladimir Fock, had independently arrived at the same equation in that same year. It became known as the Klein-Gordon equation, which was a bit of a burn for Fock. But that's often how it goes. You do all the hard work, and then no one notices. Things have changed a little since Fock's time, but the key to recognition is still visibility. And these days, that means having a website. Simple enough, you just need to write a couple thousand lines of CSS, JavaScript, or HTML, or else pay someone a few $1,000s to do it for you. Oh, and then there's the hosting costs and the maintenance. Or you could check out today's sponsor, Hostinger. Not only will they get your website online, their intuitive tools let you build it yourself. There's no need to learn multiple coding languages. The Hostinger builder can get you most of the way there with just one prompt. You can optimize the website with their built-in tools for SEO rating, logo design, and e-commerce. And once you're happy, you're online immediately on a domain that's included with the plan. That whole process is fast and straightforward, and a subscription is just a few dollars a month. So sign up now to get an 85% discount in the sale and use the code Veritasium for an extra 10% off. Just scan this QR code or follow the link in the description to get started. I want to thank Hostinger for sponsoring this part of the video, and now back to Klein, Gordon, and Fock. The Klein-Gordon-Fock equation even made its way over to one of the fathers of quantum physics, Niels Bohr, who must have been impressed, because at the 1927 Solvay conference, Bohr was chatting to a promising young physicist about what he was working on. The young man said, "I'm trying to get a relativistic theory of the electron." Bohr replied, "But Klein has already solved this problem." The young man disagreed. So who was this bold 25-year-old? He was Paul Dirac, a man who Bohr would later give the nickname the Strangest Man because he was truly one of a kind.
First time I went to Princeton, I met a couple who invited Dirac and his wife, and Dirac, for the whole meal, which lasted 3 hours, didn't say a single word. Not one word. He wasn't sulky. He wasn't angry. He just saw no reason to speak.
That's crazy.
Dirac was a man of so few words that his colleagues invented a special unit, a Dirac, equivalent to speaking 1 word per hour. Legend also has it that he liked to relax by climbing trees in 3-piece suits. And that wasn't his only strange hobby. As a student, Dirac had attended seminars on Einstein's theory of relativity, and he'd kind of fallen in love with it. He was impressed by the elegance and beauty of its mathematics. To Dirac, this got to the core of what a good theory must do. He once said, "It is more important to have beauty in one's equations than to have them fit experiment."
Do you know why Dirac was so drawn to relativity?
Einstein went in there and did it all, not all, but almost all by deductive reasoning. That made a huge impression on Dirac, right? He realized that it was advanced mathematics was really important to understanding the way that nature works.
So Dirac found a new hobby, obsessively updating classical equations with Einstein's theory of relativity, so that they would now work for relativistic scenarios as well, that are those approaching the speed of light. He later said this was like a game for him, and so it's maybe not too much of a surprise then that he was one of the people trying to unite quantum physics and relativity. Because a theory that would cover both of these would be truly beautiful in his eyes.
Dirac didn't see the beauty in Klein-Gordon and Fock's relativistic update of the Schrödinger equation. And he wasn't alone. Fellow physicist Wolfgang Pauli, after reading Klein's paper, wrote him a letter wishing his physics a speedy recovery. Pauli was known for being pretty savage, and actually the Klein-Gordon equation is useful in some cases. But he and Dirac were both concerned with one particular feature of the equation.
And that's because the Klein-Gordon equation contains this term. That's a second-order time derivative, so the wave function is being differentiated twice with respect to time. Now, remember, the Schrödinger equation also contains a second-order derivative, but that's with space, not with time. Time is just first order. So why is this such a problem? Well, think of a very simple second-order time derivative. Something like d squared y over dt squared is equal to 3. Now, to figure out what y is, the function that satisfies this equation, we just have to integrate it twice. But notice, to find the solution, we now have two integration constants, c and d. And the problem is that we can only find that if we know both y at a given time and if we know the first derivative of y at a given time. This makes sense physically if you think about, say, throwing a ball in the air. If you want to predict the ball's future motion, well, then you need to know where you threw it from, that's its position, and how hard you threw it, that's its velocity. Or in other words, you need to know both the position and the first derivative of the position.
Similarly, to predict a quantum system's future state using the Klein-Gordon equation, you'd need the initial wave function and the initial first derivative of the wave function. Now, the beauty of the Schrödinger equation was that if you knew only the wave function of a system at a given time, you could use it to determine all the future states of that system. But in the Klein-Gordon equation, the wave function no longer told the whole story. And this introduced a further problem. The probability of finding a particle in a given area could no longer be simply described by the modulus of the wave function, as it was for the Schrödinger equation. For the Klein-Gordon equation, a new equation was needed to describe the probability using the wave function, which takes a while to derive. So we won't get into that here, but it looks like this. And the problem with that equation is that, unlike the simple modulus of the wave function, it can have negative solutions, negative probabilities. How can the chance of something happening be less than 0? As Dirac put it, that, of course, is physically nonsense. So Dirac did what Dirac does best, and he set out to find his own solution that contained no second-order time derivatives. First, he rewrote the relativistic energy-momentum relationship like this, which is a linear equation, so no squaring E, that is, no squaring the energy operator, which is what gave rise to that second-order time derivative in the Klein-Gordon equation. Now he just had to solve this equation and find the coefficients alpha x, alpha y, alpha z, and beta, and he would have a solution. To do this, we can start by squaring both sides of the equation. Next, we can expand the momentum on the left-hand side into its 3 dimensions, and then expand the right-hand side to end up with this long equation. It might look pretty complicated, but there is a trick we can use. Notice that all these terms on the right-hand side are multiplied by PMC cubed, but on the left-hand side, there are no terms containing PMC cubed. So that tells us that when you multiply these coefficients together, like the alpha times beta and beta times alphas, all of that must be 0. And similarly, notice that these terms are multiplied by 2 different momenta, like px and py times c squared, which also don't have a counterpart on the left-hand side. So these alpha times alpha terms must also be equal to 0. And that just leaves this top row. These terms do match on both sides, which tells us that alpha x squared must be equal to 1, and so must alpha y squared, alpha z squared, and beta squared. So Dirac now had a set of simultaneous equations for alpha x, alpha y, alpha z, and beta that he just needed to solve. That sounds easy, right? But it's not that straightforward.
To see why, let's do some examples. So say alpha x is 1 and beta equals -1. Well, then we get 1 squared, which is 1, equals -1 squared, which is also 1, so that satisfies the top equation. But if we fill it in here, we get 1 times -1, which is just -1, plus -1 times 1, which is again -1, for a total of -2. So that doesn't work. So let's try another number. Say alpha x is 1, and now it's alpha z that is -1. Well, in that case, we get 1 times -1, so again we get -1, plus -1 times 1, again -1, so we again get -2. And in fact, if you look at this top equation, the only numbers that satisfy this relation is 1 and -1. So all these coefficients have to be either 1 or -1. But if you fill that in, then the only two possible answers you're going to get in these equations is -2 or +2. Now, the two equations that are giving problems are these two. And that's because alpha times beta is the same as beta times alpha. So you're always going to get -2 or 2. So the only way to get out of this is to somehow make the order of multiplication matter. But where do you find something like that?
Let's think about a really simple vector, say 1 in the x direction and 2 in the y direction. If I reflect this vector along the line y equals x, and then reflect it about the x-axis, I get this. But if I start again and instead reflect it first about the x-axis and then along y equals x, I get this, which is totally different. So the order matters. How do we express this mathematically? We need some way to represent transformations like reflections as a single coefficient, which means we need matrices. Matrices are arrays of numbers which encapsulate these transformations, telling us how to reflect, rotate, stretch, or squish across each dimension. Mathematically, the order we multiply them matters, since we multiply the rows of the first matrix by the columns of the second. A matrix that reflects along y equals x looks like this, and a matrix that reflects about the x-axis looks like this. And if I apply them to that original vector one by one, you can see how we end up with different results. And actually, using matrices in quantum mechanics was not completely out there. Dirac had already seen it done by Werner Heisenberg, his new, if unlikely, friend. Dirac and Heisenberg were very different characters. Heisenberg was charming and outgoing. Dirac hated socializing and small talk. Once, the two were on a cruise ship to a conference together, and Heisenberg spent a lot of time dancing with women on board. So Dirac asked him, "Why do you dance?" Heisenberg replied, "When there are nice girls, it is a pleasure." Dirac thought about this for a bit before saying, "How do you know beforehand that the girls are nice?" So they were pretty different guys, but Heisenberg had a profound impact on Dirac.
Do you know what drew him to quantum mechanics initially?
He always said that. Heisenberg gave him his start. He always said that. In later life, he used to begin lectures when he was 70, even 80 years old, with the following words.
Quantum mechanics was discovered by Heisenberg in 1925.
As a PhD student, Dirac had closely followed Heisenberg's work. And a few years earlier, Heisenberg had found that for certain properties, like position and momentum, the order of multiplication matters. So x times p is not the same as p times x. This was actually the beginning of Heisenberg's famous uncertainty principle, which says that there's a limit to how precisely we can know certain pairs of physical properties in quantum systems. It turns out that if the order of multiplication matters for two properties like position and momentum, then that means there's an inherent uncertainty in their combined measurement. The order we measure them in will change the outcome. Heisenberg's mentor, Max Born, suggested that he could represent this mathematically by using matrices, because there the order of multiplication also matters. This led Heisenberg to a new form of quantum mechanics, which was mathematically equivalent to Schrödinger's equation, but it was based on matrix algebra.
Dirac recognized something similar in his coefficients, where the order of multiplication clearly mattered. So he thought matrices might be the solution. For his coefficients, he tried 2x2 matrices, since they're the smallest, simplest matrices that could make the order of multiplication matter. He found that some worked with the equations. In fact, those reflection matrices we tried earlier worked well. but he just couldn't find solutions for all 4 coefficients that all work together.
So this is not simple. You're Dirac, one of the smartest people of the 20th century in physics, right? But it was not easy. You don't have just to twiddle with bits of the Schrödinger equation. You have to do something completely radical. His working is in there, and you could see him really struggling.
Then, Dirac had a stroke of genius. He said, "I suddenly realized that there was no need to stick to quantities which can be represented by matrices with just 2 rows and columns. Why not go to 4 rows and columns?" With these 4 4x4 matrices, Dirac got these solutions to his simultaneous equations. A matrix with 1s on the diagonal is mathematically equivalent to a 1, and a whole array of zeros is the same thing as 0. So all of the equations were satisfied. Dirac had found coefficients that worked. Now, we can substitute those matrices back into Dirac's linear equation, then rewrite the 3 momenta and alpha coefficients as vectors. And, just as we did with the Schrödinger and Klein-Gordon equations, we can use the energy and momentum operators to make both sides act on the wave function. If we substitute those operators in, we get Dirac's final equation for the relativistic free electron. The young man who spent his life looking for mathematical beauty had found, perhaps, his most beautiful equation of all.
People were expecting the solution to be horrible, and it turned out to be a thing of beauty, right? It was something you look at and you think, that is absolutely amazing. It's a pattern that Dirac had found deep in nature. Nothing like that had been seen in physics at that time.
To see some of that beauty, you only have to compare it to the Schrödinger equation, which you can see right here. Now, the two look very similar, but there is a lot hidden in the Dirac equation. First of all, it's relativistic, so it works at really, really high speeds, because it uses Einstein's energy-momentum relationship, unlike the Schrödinger equation, which breaks down there. But what's even more beautiful is that if you look at this, Dirac's equation isn't just first order in time derivatives, it's also first order in spatial derivatives, whereas the Schrödinger equation was second order in spatial derivatives. So you might wonder, well, why does that matter? Well, because not only does going first order in all derivatives solve the second order time derivative problem of the Klein-Gordon equation, it now also treats time and space symmetrically. And it becomes really important if you start thinking about relativity, where time and space are not separate dimensions. They're intertwined in a 4-dimensional spacetime. And while the Schrödinger equation had just a single component wave function, to make the wave function work with these 4x4 matrices, in Dirac's case, you actually need a wave function that has 4 components. So it will look something like this. Psi1, Psi2, Psi3, and Psi4.
The 4-component wave function means that the Dirac equation describes 4 possible states for any quantum system, which reveals something Schrödinger's single wave function didn't. An electron at a given energy level actually has 2 possible states due to different orientations of its intrinsic angular momentum: spin up and spin down. This spin creates a tiny magnetic field, so these 2 states are like tiny magnets pointing in opposite directions, and that has an interesting implication. Take hydrogen, which has 1 proton and 1 electron. Classically, the electron whizzes around the proton, but if you switch to the perspective of the electron, well, now it's the proton that's moving, and since it's positively charged, that moving charge creates a magnetic field in the electron's frame of reference. So now you've got this electron, which has its own mini magnetic field, interacting with a larger magnetic field, and that interaction will be slightly different for a spin-up and a spin-down electron. And as a result, some energy levels of the electron split into 2 closely spaced energy levels. And you can actually see this if you zoom into the emission spectrum for a hydrogen atom. Schrödinger's equation didn't predict that splitting, since it just had 1 solution for each energy level. But with Dirac's 4-component solution, the top 2 wave functions now described 2 different spin states with 2 slightly different energies.
Dirac admitted himself that he had never set out to capture spin in his equation.
I started out this work without any intention at all of bringing in the spin of the electron.
But hold on, because if an electron at a given energy level only has 2 possible spin states, then why do we have a 4-component wave function? Why are there 4 states and not just 2?
Well, that's what brings us back to that 1928 lecture at the start, the one that seemed to drive even the most well-established quantum physicists mad. because that strange man presenting his work was actually Paul Dirac, sharing his new equation with the world. It was Dirac's beautiful equation that Heisenberg called the saddest chapter in modern physics.
To understand why all those physicists were losing their minds, we only have to look at the simple case when a particle is at rest. This term right here describes the momentum. So when the particle doesn't move, this becomes zero and it drops out, which gives us this. Next, we can sub in the energy for this quantum operator to get this. So now we know that beta times mc squared must be equal to the particle's energy. And if we write out beta and multiply it by mc squared, then we find two positive solutions and two negative solutions for the energy. So negative energy solutions are baked right into the Dirac equation. This idea that a free electron could have negative energy was impossible for any of these physicists to accept. Because think about it, if electrons can have a negative energy, then that means that they could continually radiate positive energy, that is, emit photons, and drop into lower and lower negative energy states. There would be no limit to how far they could fall into the negative energy abyss.
It looked like, to many very smart people, and Dirac was smart enough to know they had a point, that this equation, it got the mass and the magnetic moment of the electron. Yes, but on the other hand, it predicts this ridiculous situation where they have negative energy values.
Right.
That's nonsense. So Heisenberg said, I give up. This is just ridiculous. So Dirac, he had in some very clear sense had to rescue his equation.
Dirac spent 3 years sticking to his guns. He tried all sorts of ways to interpret his new equation to explain where the negative energy was coming from. Then, in 1931, he proposed something radical to explain the negative energy solutions. A new kind of particle, unknown to experimental physics, having the same mass and opposite charge to an electron. We may call such a particle an anti-electron. We should not expect to find any of them in nature on account of their rapid rate of recombination with electrons. So Dirac was proposing that those four states described in his four-component wave function are a spin-up electron, a spin-down electron, a spin-up anti-electron, and a spin-down anti-electron.
When Dirac said that, people didn't start running around saying, where's this anti-electron? They just ignored it.
Yeah.
Cut to the laboratory at Caltech.
In 1932, a Caltech postdoc named Carl Anderson was working on a project trying to identify the charged particles produced by cosmic rays. He photographed the tracks these particles left in a cloud chamber containing a uniform magnetic field. Anderson noticed several instances of a similar track. It looked a lot like the tracks he'd seen left by electrons. Only it curved in the opposite direction in the magnetic field, kind of like the tracks of positively charged protons. But there was no way it could be a proton based on the length of the track. It had traveled farther in air, and therefore it had to be much lighter. It had to be something with around the same mass as an electron, but opposite charge, a positive electron, or as he named it, a positron. He actually also tried to rebrand electrons as negatrons, but that one didn't quite stick. Just 1 year after Dirac proposed the anti-electron, Carl Anderson found it, entirely by accident.
But this alone doesn't get rid of the negative energy problem. Remember what we said earlier. If any particles, like these positrons, can have negative energy, then they could continually radiate energy and drop into lower and lower negative energy states. Fortunately, Dirac proposed a solution to this problem as well, although it was a little crazy.
He theorized something called the Dirac sea, describing a vacuum as an infinite sea of electrons occupying all available negative energy states. And since no two electrons can occupy the same state, this prevents observable positive energy electrons from falling into the negative energy states. A hole or vacancy in this sea then becomes a positron. When an electron and a positron meet and annihilate, well, that's just an electron falling back into the sea and filling that hole. The theory is mathematically sound. Of course, it's Dirac we're talking about. But if you feel like it's hard to come to terms with the idea that we're floating on an infinite sea of electrons, well, you wouldn't be alone.
It's not even that crazy if, I don't know, several decades later, people find that exact model in a physical system. In condensed matter physics, you see an exact analogy of also having electrons in the conduction band and safe valence band.
Yes, that's true. That's true. But Dirac really was, out there. You see what I mean? People like, really senior people are saying, this is nonsense. But it was a way of Dirac's rectilinear thinking, well, maybe this, and then it drove him to antimatter.
Thankfully, in 1941, a Swiss physicist named Ernst Stuckelberg had a clever idea. The wave function contains a term that looks like this, where energy is multiplied by time. So we can see that if we just change the sign of time when the energy is negative, then we get the same result, because a negative multiplied by a negative gives us a positive. Stuckelberg took this and he suggested that negative energy electrons traveling backwards in time are mathematically equivalent to positive energy anti-electrons, that is, positrons, traveling forwards in time.
A few years later, around 1948, Richard Feynman took this idea and used it in one of the most powerful tools in modern physics, the Feynman diagrams. In his sketches of particle interactions, he showed antiparticles traveling the opposite way to particles, backwards in time. It was a brilliant trick. Negative energy solutions no longer had to mean there was negative energy or a Dirac sea. They simply indicated the presence of an antiparticle. We now know that there's a corresponding antiparticle for every subatomic particle, with the same mass but opposite charge. So the proton has the antiproton, the neutrino has the antineutrino, and so on.
According to his friend Heisenberg, that was the biggest leap in 20th century physics, to say there's a whole slew of antiparticles corresponding to particles. And Dirac got that through this crazy model.
But all is not solved. This new anti-world introduces some big questions about the very nature of our universe. Because particles and their antiparticles are equal and opposite, when they come together, they annihilate and produce two photons with energy equivalent to their mass and kinetic energy. And this process is reversible. Two photons with the right energies can produce a matter and antimatter pair. This is called Bright-Wheeler pair production. During the first moments after the Big Bang, the universe was hot, dense, and full of these pairs popping into and out of existence. If an equal number of matter and antimatter particles were created, you would expect them to all annihilate each other in this dense environment, leaving behind only energy. But that didn't happen. We ended up with a universe full of matter. If we work backwards from how much matter and antimatter is in the universe today, it's actually estimated that only 1 particle per billion of matter needed to survive this hot, dense era and not get annihilated. That tiny difference would give us the makeup of our universe today, where matter dominates.
So what allowed that 1 particle per billion to escape annihilation? Why did matter win out over antimatter? Well, that's a pretty big question with some not so simple answers. So we're doing an entire second video where we have some pretty spectacular stuff happening. We're getting into the beast. It's absolutely insane. I feel like I should not be in here. So you're making anti-atoms.
Yes.
It's so cool.
Dirac is probably less well known than people like Heisenberg or Schrödinger, but his contribution to quantum physics was immense, and he was recognized for it. He shared the 1933 Nobel Prize with Schrödinger for the discovery of new productive forms of atomic theory. And perhaps this gave strange, quiet Dirac some newfound confidence, because that physicist in the audience of his 1928 lecture at the start, Eugene Wigner, actually became a reasonable friend of Dirac's, and in 1934 introduced Dirac to his sister, Majit Wigner, a woman who would change Dirac's life, perhaps more than any equation or Nobel Prize.
They were antiparticles, right? They had completely different personalities. He had almost no empathy, right? And he knew it. She had buckets of it. He hardly talked, she couldn't stop talking. You could just go on like they are completely different people. But the marriage did work. My great friend Lilia Harris Chandra, who knew them, she came out with a great line, which is, he gave her status, she gave him a life.
So I guess there is one particle-antiparticle pair that never annihilated.
Hey, one last thing. In case you didn't already know, we just launched the official Veritasium game. It comes with 800 questions and it's the perfect way to challenge your friends. Every time we play it at Veritasium, things get a little bit heated, and that is so much fun. If you want to go check it out, then head over to our Kickstarter where you can pre-order your own version. And right now we've enabled global shipping, so no matter where you are in the world, you can get your own version. We're coming close to the final few days of the Kickstarter campaign, so this is your last chance to get your hands on the exclusive launch edition. So if you want to support us, head over to Kickstarter by clicking the link in the description or scanning this QR code. I want to thank you for all your support, and most of all, thank you for watching.